To continue the solution stoichiometry portion of chapter 4, we're going to look at a precipitation reaction. So we're going to look at the precipitation of barium phosphate. Okay, so for this, we're going to precipitate barium phosphate from a solution of barium chloride and a solution of sodium phosphate. This is a nice exchange reaction where barium and sodium swap places. So we form barium phosphate, solid, and then we form 6 NaCls at the end that remain aqueous. So here is our precipitation reaction. Okay, so we're going to solve for how many grams of barium phosphate are going to form when we combine 50 milliliters of a 1 molar solution of BaCl2 with 50 milliliters of a 1.5 molar solution of Na3PO4. Okay, so again, we want to know what mass of sodium phosphate, or excuse me, what mass of barium phosphate is going to form. Okay, so I need to figure out which one of these is my limiting reactant and which one of these is my excess reactant. Okay, so we'll start with our barium. So if we look at BaCl2, we're going to take our volume, so our 0.0500 liters. We're going to multiply that by the molarity. And now we're going to use a mole ratio. So we're going to use 1 mole of barium phosphate for every 3 moles of barium chloride. Okay, so if we solve, all right, so if we solve, we're going to end up with our 0.05 times our molarity of 1 and divided by 3. So we have 0.01666 repeating 7 of Ba3PO42, and that's moles. Okay, so if all of that reacts, that's how much barium phosphate we can make. We're going to do the same now with our sodium phosphate. So Na3PO4. So we do the same thing with volume times the molarity. And now a mole ratio. 1 mole of our barium for every now 2 moles of sodium phosphate. Okay, so if we solve for that one, our 0.05 times our molarity of 1.5, now divide that by 2, we have 0.0375 mole of the Ba3PO42. Okay, so if we compare, the barium chloride produces much less, so we know that this is our limiting reactant. So this is our limiting reactant, and this is the amount of moles of barium phosphate. Okay, so now we just need to find what mass. So we're going to take the moles and multiply it by barium phosphate's molar mass. which is quite large. It is a nice whopping 602 grams of Ba3PO42 for every 1 mole. So when we solve for that, we get 10 grams of barium phosphate can be produced by combining those two solutions of sodium chloride, barium chloride and sodium phosphate. Okay, so this is how a limiting reactant problem, like a basic limiting reactant problem, will work in a precipitation reaction where, again, same thing, solve for our product. We're going to see which one is our producing the less amount. So that's our limiting reactant. So we know our barium chloride is limiting. It's going to determine how much of the solid we make. So now that we have those moles, we can just multiply it by the molar mass there. This is kind of a standard, stoichiometry problem. So if we look at a stoichiometry map, in a reaction, most often we're going from moles of A to moles of B. Okay, so we have something like a reactant and something like a product that we're going from one to the other using our reaction. So we know for this we're using our coefficients. So we're using the coefficients of our reactant or the balanced chemical equation. Okay, so in chapter 3, we talked about how the way to get here is if we start with, say, mass of compound A. So if we have mass of compound A, we know that we use the molar mass of compound A to get moles. Then we can build our mole ratio and get compound B. And then if we wanted, for example, we could solve for mass of compound B. So this is what we did a lot in chapter 3. And again, this is the molar mass of compound B now. Okay, so I kind of drew these down and it's kind of a little weird, like, hey, why is that? We learned something in this chapter, another way to do that. We could be giving volume of A in solution. And we can use the volume of A in solution to find moles of A by using the molarity. So if we use the molarity of A, we know that molarity times volume will give us moles of A. And then we can use our coefficients to find moles of B, just like we did up here. We used volume and molarity to find moles, and then we used our mole ratio. So same exact thing here. Okay, so the first stoichiometry problem we did, we had that acid-base one. So this we can also find volume of B in solution. And if we need to know volume of B in solution, we're going to use the molarity. Okay, so now we have all different combinations we can use for stoichiometry. So in the problem we just did in the precipitation, we had volume of reactants, we found moles of reactants, moles of product, and then we went mass of product. So we went from solutions to solids. We can go from solids to solutions, possibly. That one might seem a little weird, but I don't know. You never know. It's possible. So we have all different paths now that we can take, but it all comes down to, again, to get moles here, that's molarity times volume. So again, remember, for this chapter, our good way to get moles is molarity times volume. When we're dealing with mass, to get moles, that's your mass divided by your molar mass, which allows us to go from mass to moles or volumes to moles. Okay, so that's our solution math there. Okay, so one more problem from chapter 4. And then this one should be about it. All right, so for this one, we are going to look at the reaction of K2SO4 plus silver nitrate, and we are going to produce potassium nitrate and the precipitate silver sulfate. Okay, so this one, I do have silver sulfate here. So if you go to your solubility chart, this one might not show up. This one is mostly insoluble, but kind of sometimes is left off of solubility charts. But this does actually produce a solid. But again, you're not going to find that on your solubility chart. It's not included on all of them. Oh, this guy is aqueous. Okay, so we're going to calculate the mass of silver sulfate. And we are going to do that from an initial volume of 33.5 milliliters of potassium sulfate that has a molarity of 0.725 molar. Our silver nitrate, we're going to use 20.4 milliliters, and it has a concentration of 0.843 molar. Okay, so in this problem, we want to solve for, so we want to know, 1, the mass of Ag2SO4 that we are going to make, and 2, the concentration of each ion, where the brackets there stands for concentration. Okay, so I'm going to set up a table to help me solve this. Because I want to, if I have to calculate the mass of each ion left, that's a limiting reactant, excess reactant problem, and I want to set up a table for that. So I'm going to take this and break it apart into total ionic equation here. So that's 2K plus SO4, 2 minus, plus 2 Ag plus 2 NO3 minus, arrow 2K plus 2 NO3 minus plus Ag2 SO4. Solid. Okay, here is my total or complete ionic equation. Okay, so now I'm going to concentrate or calculate the initial concentration of each. I'm going to make an IRF table. Okay, initial, what's going on in the reaction, and then what I have as a final. Okay, so I'm going to go ion by ion so I can figure out what's my limiting, what's my excess. Okay, so first of all, I can for sure look and see that I have potassium here and potassium here. So I know that this, I'm just going to kind of draw a line through those really, really lightly. I know that those are spectators. So what that means is these are ions in solution on the reactant side and on the product side. Okay, if I look, I see that nitrate is the same. So nitrate is the same. So their sort of entries into the table are going to be identical on each side because they're floating in a solution continuously through the whole way out. Okay, so what that leaves me with is the other two ions that are left, my sulfate and my silver. So one of these is going to be the limiting ion and one of them is going to be the excess ion. Okay, but let's work on filling out the table. Let's start with potassium. Okay, so potassium is coming from potassium sulfate, so that is 0.0335 liters times 0.725 mole of K2SO4 per liter. And since I need potassium and not the molecule here or the compound, I know that 2 mole of potassium for every 1 mole of K2SO4. Okay, so when I solve for my concentration of potassium, I have to have that mole ratio. That 0.0335 times 0.725 and then times 2. So for potassium, we have 0.048, we'll call it 6. 0.0486. Okay, so next we have sulfate. Okay, so SO4, 2 minus. We're going to use the same, it comes from the same compound, so we're going to have the 0.0335 liters times the 0.725 mole of K2SO4 for every liter. For this one, our ratio is 1:1, so we get 1 mole of sulfate for every 1 mole of K2SO4. Okay, so for this one, we're going to have half of that because we just have the one ion. We had double the ions there, so 0.0243. Okay, so this is in units of moles in the table. Okay, so that gets us our first two values there. So we have our first two entries. So now we're going to look at the silver nitrate. Okay, so silver and nitrate. So this one is nice. We're going to get to do a little bit less work for this one. So since these ions are both 1:1 and their mole ratios would end up like this, if I find the concentration of this solution, I'm going to get the concentration of each ion. So that is nice. So Ag plus and NO3 minus will be the same. Okay, so we're going to have 0.0204 liter times 0.843 moles per liter to give us our concentration, 0.0204 times 0.843, 0.017, we'll call it 2. Okay, so that's this one. Okay, oops. So we have, we solved here, so now we have our silver and we have our nitrate here. Okay, so I said this was a spectator. I said this was a spectator. So again, they're the same on each side, so I make kind of this box here. All of their values are the same. They don't change. So it's not involved in the reaction, so we have 0.0486. Not involved in the reaction, 0.0172. This didn't change, we'll call it 486. Nothing happened, 0.0486. And the nitrate, 0.0172. Nothing happened, 0.0172. Okay, so once we find out the spectators, we can fill out their chart. Nothing happens in the reaction. Whatever you have initially is what you have in the final. Nothing about it changes. So we just populate that in. Okay, which leaves us then our two ions actually participating in the reaction to form that precipitate. So we need to see which one of these is the limiting and which one of these is the excess. So if I look, I'm going to need double the amount of silver because it has that coefficient of 2. Looks like I don't even have anything close to that. It appears that silver is my limiting reactant, but we can go ahead and kind of look. So let's convert silver and see how much sulfate we need for that. So 0.0172 mole of silver. So when it reacts, we need 1 mole of sulfate, and for that we need 2 mole of silver. Okay, so we have our 0.0172 divided by 2. So we need 0.0086 mole of sulfate. Okay, so for all of this to react, that's how much of the sulfate we need. If we look up in our table, we're given way, way more than we need. So we have plenty. So we confirmed that what we thought is true. This is our limiting reactant. So we know we're going to use all of it. And we're going to have none of it left. And now we're going to call this the limiting ion. Okay, which means this one is the excess. That's the excess ion. Okay, so this one's all done. So we know we're going to use 0.0086 worth of that ion in the reaction. So we're going to go 0.0243, subtract our 0.0086, which tells us we have 0.0157 moles of sulfate left in excess. Okay, so now we need to look at our product here, our silver sulfate. So our coefficient here is a 1. So our coefficient for sulfate is also a 1. So its value, or its entry for R, is identical. So this value is going to be the same here. So we have 0.0086 moles produced, 0.0086. Okay, initially we have no solid. Okay, again, if we took this, which we know is used in the reaction, and made our mole ratio, we get this. Or if we started with our silver, which we know is our limiting reactant, and made our mole ratio, we would get this here. Okay, so let's solve for mass of silver sulfate. So I'm going to take this moles and multiply it by the molar mass. So Ag2SO4, that's going to be my 0.0086 mole multiplied by the molar mass, which is 311.8 grams Ag2SO4 for every 1 mole, which gives me 2.68 grams of Ag2SO4. And so that is the mass of silver sulfate. Okay, so now the last part of this, we want to know the concentration of each individual ion. Okay, so now that's where we're up to. So we know that concentration equals moles per liter. Lucky for us, right now we have all of that right here. So filling out this table, we know how many moles of nitrate, we know how many moles of sulfate, we know how many moles of potassium. We're just going to need to take that and turn it into a concentration. Okay, so first thing we want to determine our total volume. So after we mix, we have the 33.5 milliliters that we mix or we add to the 20.4 milliliters to form that precipitate. So we have a grand total of 53.9 milliliters, which is 0.0539 liters. Okay, so our concentration of potassium ions in solution is going to be our moles of potassium that we're going to grab from the table, 0.0486. Divided by our volume to give us our concentration of potassium as about 0.901 molar of potassium. Okay, we're going to do that now with sulfate. So our concentration of sulfate. So we're going to grab the moles from the table, the 0.0157 divided by the 0.0539 liters. So our concentration of sulfate ions, 0.291 molar of SO4, 2 minus. Oops, sorry about that. So moles per liter to give us our concentration of sulfate. And then finally our nitrate, our NO3 minus. So we're going to get our concentration of nitrate, 0.0172. And divide by our volume. Give us our nitrate as 0.319 molar. Okay, so this is essentially our two ions here that were spectators. What really happened with them is that they were diluted. So you could have used the formula for dilution for these also and skipped their entry in the table, because really that's all that this amounted to, was the potassium ions were in a volume of the 33.5 milliliters. Now they're in the volume of 53.9 milliliters. So potassium was diluted. The nitrate was diluted as well. But for the sulfate, remember, some of this was used in the reaction to make the silver sulfate, and then some of it is left over. So what we did here was figure out what was left over in excess and turned it into the concentration of sulfate. So that's how a limiting reactant problem will work in a solution stoichiometry problem. Now, instead of having limiting reagent and excess reagent, it's more appropriate to think of, like we had here, limiting ions and excess ions. Okay, so once, and then the other ones like we had here turned out to be our spectator ions. So we had ions involved in the reaction, and then we had spectators.